Great. Well, I first did want to thank the organizers for inviting us all out to balmy Santa Barbara. I know, in the East Coast we're having this polar cyclone bomb vortex, whatever's going on, and our heat went out the day before I left. So I'm not earning any husband points being here this week. So I work, I'm primarily appointed in the Material Science Department. I have a joint appointment in physics. I work on various materials problems that involve non-equilibrium systems. I'll talk mostly about glasses, deformation in glasses, but Sri said I should talk about what my more general interests are, so I also work on things related to friction, charging of cathode materials, and some dislocation work in magnesium alloys. But I think this is the topic that's most relevant to the program, so I'll talk about deformation in glassy materials. And so just before I get started, so this is the work mostly of Adam Hinkle, though Darius and Dewey have been playing some role. Adam just graduated, he's now at Sandia Lab. Dewey is involved in an extensive biological experiment at the moment that you can see there. And then the first part of the talk will be collaboration with Sylvain Patinet, a former postdoc in my group who's now at ESPCI, and Damian Vandenbroek there. And then the second part is a collaboration with Chris Rycroft and Mike Shields, who's a civil engineer in our engineering school. So, the general topic I'll talk about are what happens when you deform glasses. Or more generally, amorphous solids. And what I mean by amorphous solids are just any sort of material that has no long-range crystalline order. And it turns out that almost every kind of material can, under the right circumstances, be produced in an amorphous form. That includes silicon, which can be used to form solar cells, these dental implants, which are made of some polymer, and what I'll talk about mostly, which are metallic glasses, which really were developed only more recently in the 1960s, since metals really like to form crystals. But under the right conditions, with the right alloy, quenched at the right speed, you can create a metallic glass which looks just like any other metal, but has some very interesting properties, which make it potentially of industrial application. Those are that it is high strength. Since it doesn't have any dislocation defects built into the structure, they get to much higher stress before they start to exhibit plastic deformation. In addition, because they don't have any grain structure that develops, they're easy to form through near net shape forming. So basically you can heat them up to near the glass transition temperature. They become highly viscous, and you can push them into a mold, and you don't have the problem of shrinkage associated with the first order phase transition, or the grain structure interacting with the mold, or what you're doing to the material. So they're potentially industrially interesting materials, but they have some bad failure characteristics that we'll talk about. But I think amorphous solids are generally of interest, or should be of interest, for the purposes of this program, because although we have this tendency to think of amorphous solids in glasses as just having some disordered structure that's nebulous and difficult to characterize, in fact, they actually have quite well-defined structures. It's just that we are not very good at describing them. And so this is a particular example I just wanted to highlight. It's not really related to the rest of the talk. It's a metallic glass. It's this particular alloy. And this was a study, an experimental and computational study that was done by Howard Shang, Evan Ma, and some others. And so what they're showing is that this is a glass in which you have a phenomena called polyamorphism. So basically there are two distinct amorphous structures that can be formed in this glass. And you can switch between the two. In this case, by imposing pressure. You have one high-density amorphous phase and a low-density amorphous phase. And by applying pressure, you can actually cause a transition between the two amorphous states. So even though we find it difficult to characterize the structure of the glass, it's possible you could create a single glass, a single composition, and have regions that are in different states. And thereby you could store information.
So I'd like you to sort of comment on the state of, certainty about this polymorphism in metallic glasses, or metallic glass formers. And just let me say a couple of things to prompt.
Okay.
So one is, if I'm not mistaken, is the claim that compositionally these two forms are not different.
That is the claim in this paper.
Yeah. If there was a compositional difference, it's not either surprising or difficult to understand if you have multiple amorphous spaces, because mixtures do that all the time. So the surprising thing should be that they're the same.
That they're the same composition, but but seem to have two distinct phases.
The second thing that's not clear to me is how closely is it understood to be associated with electronic structure changes.
Right.
That's one way in which, in these systems, you can imagine.
Yeah, and well, in this case, that was the claim. I mean, this is not really my area of expertise. It was just something I wanted to highlight as sort of why glasses are relevant. But in this case, that was exactly the claim they were making. They had done electronic structure calculations of a low density and high density structure, and I believe the next figure in this paper is the band structure, showing how the band structure differs from the high density to the low density configuration. So that was...
no, that's not... I mean, that may well have been... I mean, I'm sure that's what they showed. But the point... No, but it's sort of a chicken and egg thing, because if the structure is different, if you go band structure calculation...
It's going to be different.
See differences. But what I was asking was more, if you have sort of valency changes, or something that's sort of an electronic structure change at the single atom level that induces different bonding and therefore a different structure phase. So.
Right. This is beyond my expertise in this particular area. I just wanted to put this up as something that's out there in the glasses material about the potential of storing. One way to potentially store memory in a glass.
There is some skepticism.
Yeah. I'm not necessarily endorsing this. I'm just saying it's an area of active study. But I'm going to talk about another way in which one can potentially store memory in a glass. And this came up yesterday, one of the questions at the end of the talk in the context of crystalline materials, that in crystalline materials there's a well-known effect called the Bauschinger effect, which is connected to what we sometimes call kinetic hardening. So the idea is, if you take a metallic material, a crystalline material, and you deform it in one direction, it hardens. So that means if you unload it and reload it in the same direction, it behaves more or less elastically up to the stress to which you loaded it the prior loading. But if you take that material after unloading, and rather than load it in the same direction, you load it in the reverse direction, for some materials you find that it's softer in the opposite direction. And so this was also observed in simulations. I think the first sighting I know of it was by Sid Yip, Ali Argon in 1989. So this was the data from that paper. And you see they load the system, then they unload it. Upon unloading, it's fairly linear. But then when you load it in the reverse direction from zero, you see it's considerably softer. And then we had seen this back when I was doing my grad work, where we would load a glassy system using molecular dynamics simulation, unload it, reload it. It would behave more or less elastically on reloading, but if you loaded it in the opposite direction, you would see it was softer. So somewhere in the microstructure of the material, there's something that's encoding the fact that I've been loaded in this particular direction before. And that if you load me in that direction again, I'm going to be hardened up to a high stress. But if you load me in the opposite direction, that's not going to be the case.
So I'm just a little bit slow, but what do you mean by softer? I mean, is it that they go to the same magnitude of the shear stress in both directions?
Well, you can...
is that what you mean by...
Right. But if you look for when it turns over, when it deviates from a sort of linear loading, right, that happens earlier in this direction than it does in this direction.
At a smaller strain.
At a smaller strain. A smaller stress. Smaller stress.
Softer doesn't mean...
And smaller strain.
So softer doesn't mean a lower modulus, but an early onset.
No, because we're talking about plastic response, not elastic response. It's not that it's It's not that it has a lower modulus in that direction, it's that it has an earlier yield stress or a smaller yield strain also.
Are these experiments done by applying the stress and measuring the strain, or by applying the strain and measuring the stress?
I'd have to go back and check this one. This one was done by applying the stress and measuring the strain. So this was ramp up, hold the stress, lower it, hold the stress at the same level again, lower it, then hold the stress in the opposite direction. But you can see these things also under strain control.
But that's just a theoretical picture.
This is, well, no, this is an MD data plus theory.
Yeah, the top
Anyway,
one is,
so, what?
the top one is a theory picture? Or?
No, this is the applied loading. This is the applied loading.
And just to make sure, it's the fact that the dashed line coming down is curved at just a little bit. Is that region
Yeah.
right there?
So this
What
one
you
is
might
this is linear,
and
and then this one is curved.
I see.
Right.
That's the point.
Yeah. Yeah.
It starts to yield at a smaller stress.
Right. Okay. So what could be the thing that's encoding this information in the structure of the glassy material? Well, so there had been theories quite early in the late 70s by Franz Papen and Ali Argon that there were things called flow defects or shear transformations that happened in the glass when they were subject to shear, and these are images from the work I had done back as a grad student. And you can see, if you look in the glass, that there are regions where here this is a small close-up of a larger sample of a 2D binary glass being loaded, in this case being compressed along this axis and extended along this axis. And you can see that there's this one sort of cage of large atoms surrounding a bunch of small atoms that collapses in just that way. So you can get small local regions of the glass that undergo sort of mechanical collapses that lead to irreversible deformation. And here's another one from a different region.
Can you comment on the force law used? Is this Leonard-Jones?
This was Leonard-Jones. This is just a binary Leonard-Jones 2D system in this case. And all the systems I'll talk about today are similar in that some of them will be 3D, but they all have both repulsive and attractive parts to the potential, which may be very important. Okay, so one question that's persisted has been, what are these things? Can you just find them a posteriori by looking at what happened to the atoms in the glass once you deform the system, or can you actually find them in the structure? Can you a priori go into the structure and locate, this is how many of these defects you have, this is where they are, this is the stress they're susceptible to in the structure? Did you have a question? Or? Okay.
Well,
Okay.
so free volume. Are you going to say something?
So yeah, I'll talk about free volume a bit later. Yeah. Okay. So then the picture that had developed from this and that we've been working on is that we can write down a constitutive theory. You know, if we have a theory of the micromechanics of what's going on in the glass, then we could use that as a basis for coming up with a theory of how the glass is going to deform. And the basic cartoon of the theory would be that if we take a bulk material and we apply some load to it, some stress, that there are these defects, these point defects essentially riddled throughout the glass. They have different orientations. And then under the effect of that applied stress, some of them are able to flip to align with the applied stress. But also in the process, there's plastic work being done, so some end up getting annihilated and others are created in regions that previously weren't deformable. So that was the picture that we had used to develop this constitutive theory, and I'll talk more about the constitutive theory later, but it all hinges on the existence of these sort of local point defects controlling the deformation. So one big question, I think, in this field is, can this hypothesis that deformation in glassy materials are controlled by point defects of this kind be confirmed by atomistic simulation? And so one question you could ask is, are they Eshelby-like? So one thing that's been noted about them is that there's been the expectation that they behave as if you've put an inclusion into an elastic medium. That if you have deformation locally in some small region of the material, this should be equivalent, according to Eshelby, of taking out a region of the material, taking it through a deformation, stuffing it back in the hole, and then letting it go, because it's constrained by the surrounding material, and that should have a particular elastic signature. that you should be able to see in the material. And so there's been some recent work on this that I think is really exciting that I'll show in a moment. And then there's the question of, okay, then can we go into the material and by looking at the structure or other aspects of the material, can I tell you where are these defects, what are their thresholds for undergoing rearrangement, et cetera. And so there have been a number of different works trying to do this in various different ways. There have been a bunch of attempts to use the linear response of the material. So in particular, to look at the phonon spectra, to look at the vibrational modes in the material and see if regions of the vibration that are susceptible to soft vibrations are related to deformation. There's been an attempt to look at topological short-range order, bonding, things of that sort, short-range spatial correlations, and the local yield response. And so this is the most recent work by us, but I'm going to quickly jump through these things and show you them in a bit more detail so you have an idea of what's going on in the field. Yeah?
I guess the first bullet that you have is a demonstration that there are defects which are of this kind.
Mm-hmm.
Not necessarily that all defects or the relevant defects are of the SLB type, right?
Well, I'll show you exactly what. Okay. Yeah. So this is from that work. So this is work by, amongst others, N. Tanguy and David Rodney and some collaborators. And so what they did was they took a simulation of, in this case, it was a silicon glass, so amorphous silicon, and they deform it in shear, and then they try to extract as they're deforming it. So this is still a posteriori. They're not going into the structure and trying to look for the defects from the beginning. They're shearing the system and they're looking for where do they see deformations happen in the material. And then they use the fact that, according to Eshelby, there should be a particular signature of this elastic event, or this plastic event, if it's surrounded by this elastic field because it's embedded in an elastic medium. And so this is showing the displacement field that one expects around an Eshelby inclusion that you see in their atomistic simulations, and also the stress field that should develop around one of these inclusions.
Like, are these d-squared min plots? Or
No, I believe these are displacement. I think one of these are X and Y displacement. And the color is, in this case, it's from 0.0028 angstroms to 0.0, I don't know. They lost some significant figures here. I'm guessing that's supposed to be minus 0.0028. And then these are stresses going from half a megapascal to negative half a megapascal. So these two are the stress fields. So basically what they're doing is they're shearing the material. They're looking to see when rearrangements happen. They then use the elastic signature, basically the Green's function associated with one of these these plastic inclusions, to analyze what STZ just happened, how big is it, where is it. And then they infer from that how much deformation should have happened at the boundary and how the stress should have dropped. So they're getting the STZs out of direct observation of the simulation, but then from that information they're trying to reproduce the stress strain curve. So they have the stress that they've measured as they sheared the system by measuring the stress at the boundaries of the simulation, and then they have the stress they've sort of reproduced by adding up a series of Eshelby events that have a discrete effect on the stress in the system.
Continuous displacement or finite?
Yeah, these are, I believe, athermal quasi-static. So basically they take the system, minimize the energy, impose a shift of the boundary condition, minimize the energy again. So there's I don't believe there's any thermal noise. It's just what we call athermal quasi-static shearing in this case.
I'm sorry, can you just say a little bit more what this Eshelby thing is?
Sure.
I'm not...
Yeah.
Right.
So is there chalk? Oh, here. So I don't know if maybe I need light, but...
No, it's nothing.
No, that'll be okay. Okay, just a quick. So the idea here is that, so what Eshelby said is that if I want to understand many different problems where you have something happening locally, that oftentimes can be decomposed into a sort of set of operations where you you describe a circular, in his case, an ellipsoidal boundary. You take this out, right? So now you have this, and then you have the material that has no, then you take this through some kind of strain. So let's say I turn this into an ellipsoid, right? Then I shove this back in the hole, right? But to do that, I, of course, have to squish it back to being a circle under some kind of stress. So I can turn it back into a circle, but I have to hold it under stress to turn it back into the circle. I can put it right back in the hole. Then I have to release those stresses. And so what ends up happening is, it turns back into an ellipsoid now. But there's some compression here, tension here, tension here. So there's a stress field associated with the elastic medium accommodating the new shape.
And you've done something particular to the thing you've taken out, or is it somehow a homogeneous medium that you're sticking back in?
You're just assuming that you're applying a uniform shear strain, irreversible shear strain to the body to turn it from a circle into an ellipse. And then, question?
No, I mean, I think the way you said it, it's a little bit tricky.
Is it confusing?
In the original formulation, you take an ellipsoid, you insert it back in a different orientation, which actually gives you this effect. And except for the cutting and pasting, everything else is linear elastic. Linear elastic.
So you're not taking account of whether...
Well, except for this transformation.
Right. I mean, because you said you turned it back into a circle, but I don't think so. You put it back as an ellipsoid, different orientation, because if you were to turn it back into a circle, you just flipping.
Well, but you...
No,
yeah,
so
I mean...
Michael said it, you have to imagine that you somehow magically change the shape while retaining it as an unstressed elastic object.
Well, no, here it's stressed, right?
No, once you insert it, it becomes...
Oh, no, once you put it in and you release then it's stressed again. Yeah, okay.
So, Michael, is a dislocation in a 2D crystal within this class of deformations?
Not really, no, because dislocations are extended line defects, right? And this theory has to do with compact, either two-dimensional ellipses or three-dimensional ellipsoids.
What about a dislocation in a two-dimensional crystal? Would that be within this class?
History is exactly right. This is purely elastic calculations, pencil and paper elastic calculation, and not an easy one as it turns out. So.
But I think...
there's no sense in this of any sort of planes of atoms, discrete structure. So all the sort of the ideas that underlie what a dislocation is, they're not really in this picture. It's just...
It has a far field strain, I guess. And
yes.
The question is whether the far field strain of a dislocation is like the far field strain here.
It dies off more slowly.
I think a local slip, if you have a local slip, the far field stress pattern is quite similar to that, I think. Isn't that right? If you had your dislocation move by a little bit, that would be corresponding to a local slip in a crystal. I think the far field stress pattern of that is quite similar to this. Isn't that right?
I'm not sure, but it might be.
Maybe in 2D.
Yeah. Well.
Yeah. I mean, in the 3D, this dies off faster than the dislocation stresses would die off. But in 2D, it's possible it would be similar.
Yeah, like for example, if you have like an earthquake fault, and you have a little slip or something that's just a patch rather than a line.
Right.
I think then it starts looking like that.
Mm-hmm. Perhaps. Okay. Other questions about?
No, I think just to finish this, about the dislocations, I mean, the question is whether, okay, so the proposal as it's being discussed now in this amorphous solid context is that you always imagine a plastic event as something localized, and the far field consequence of that is the Eshelby field, and that's supposed to be generic. Whereas even if you can construct dislocation structures which would be localized in space with sort of a far field strain, a strain field which may or may not look the same. I guess that is not a general description of a dislocation.
It's good.
Well, so perhaps it will
Spatial
be,
pattern of energies.
so perhaps it will be more similar to having, say, a neutral dislocation pair at some distance.
Exactly. No, that's what we're
Because
talking
you need
about.
to have.
But that's a particular construction where you can
Sure.
make it localized.
Yeah.
But that's not generally what a dislocation pattern will look like.
Right.
So.
But it does lead to perhaps an analogy that one could think about, at least in 2D. Maybe an STZ is almost like a little dislocation pair that forms and separates one lattice position, but that's all it can do because there's no long-range order. So it can't travel along some existing lattice plane. It doesn't exist. So it's just can separate or go back. So it becomes like a point defect.
So this is probably in the sort of the not elastic branch, but in the branch before the union, right? Or what you see.
Well, here they have both. I mean, you have. Oops, sorry. Here you have. Here it's more or less elastic. Then you have some sort of hardening regime. Then they get softening, where they have some kind of more profound stress going on. Probably, I don't know, maybe some amount of localization.
I'm saying this.
Oh, this particular image.
Is probably from a very
Perhaps.
small strip.
Maybe taken from around here. Yeah.
Because you said it's supposed to always be in the linear elastic regime.
The assumption is always that there's some local event that happens and the material around it is behaving linear elastic relative to that change in the structure.
So the FLB construction is the cartoon of a plastic event. So it's the simplest description you can think of. Everything remains elastic except this radiation.
Okay. So then the next set of questions we had were, okay, can we find these defects in the structure of the glass a priori? Can we analyze the structure in some way to find them? And so this was work by Lisa Manning and Andrea Liu. What they would do is look at the phonon spectrum. So take the Hessian of all the interactions between the atoms, find all the eigenmodes, plot out the frequencies of the various eigenmodes, and you get the typical boson peak, right? So here you have down at low frequency, you have plane wave modes dominating. And then as you go up, you get more disordered modes. But what you see is that in the amorphous material, these plane wave modes are not pure plane wave modes, sort of admixed with whatever the plane waves are. There are some regions that seem to be undergoing slightly more deformation, that are a little floppier or softer than the surrounding medium. And so what they decided to do was look at these modes below the boson peak, look at the eigenvectors, and pull out the atoms that disproportionately move in the eigenvectors for these low frequency modes. So there are like a few atoms, so just going back here. Like there are a few atoms that are maybe displacing more than the ones that are just engaged in the plane wave. Can we highlight those? And then they notice that those tend to be activated more strongly in many of the in the low frequency modes. So when they did that, they could pull out some of the atoms, and this is another two-dimensional system, some of the atoms is participating disproportionately in the low frequency phonon modes, and then they would try to correlate those with where the system deformed when they sheared it at the boundary. And they see a reasonable amount of correlation, but somewhat difficult to directly relate it. In particular, you can see that one of the problems they ran into was that you can pull out the atoms that are more floppy, but then dividing those into discrete defects is very tricky.
Michael, so if I imagine that there is heterogeneity in the local sort of elastic modulus, if I were to then deform it with a given stress, probably isn't it sort of tautological that you would have different degrees of displacement?
Yeah, sure. I mean, you would have, so this could, one could think about this as local elastic heterogeneity, and there have been other studies where people have tried to relate this to, is it related to low local shear modulus? That's another possibility, and I'll show some data on that in a bit, but yeah.
This doesn't yet say anything about plasticity.
Well, it does in the sense that the analysis they're doing really has nothing to do with plasticity. It's really just analyzing the linear response of the material, right? The only thing that has to do with plasticity is that then they deform the system at the boundary and they ask, does this signature in the linear response correlate with where you get plastic deformation?
Yeah, they're asking where is the energy landscape flattest. What I really want to know is not how flat it is, but how big the energy barrier is.
Right,
so
exactly.
They're related, but they're not the same thing.
Right, it's not clear that one follows from the other, so it's worth checking. I mean, and there's an idea that maybe there's a, I mean, the way Lisa describes it, I think, is maybe there's sort of a cutoff criterion that you think there's a maximum deformation where if you get two particles to separate more than a certain amount, like a Lindemann criterion or something, then they undergo some kind of rearrangement, and so the soft regions end up having more stretching, more likely to get to this point earlier. That's a sort of hand-waving argument.
There's sort of a dual problem, which instead of looking at like the velocities of all the particles, you can look at the sort of tensions in all of the springs connecting the particles, and that also gives a kind of criterion for looking at places where the material is likely to fail. Do you know if they looked at those sort of self-stresses as well?
Well, here they are.
I mean, associated with each of these eigenvectors, you also have a sort of a dual eigenvector, which is a matrix which is related to the Hessian in a way that I can explain, but it gives sort of a set of tensions that you put on all the bonds.
Right. Not to my knowledge. I don't think they've analyzed that.
Which I know is being used in other kinds of materials to look at where it's likely to fail.
Yeah, that would be very interesting. But yeah, I don't know of any work.
They didn't do anything with that, and it might
not
also
to my
be more
knowledge.
related to like the energy barrier too.
Right.
So generally, I mean, in these systems, because you don't have an elastic network to work with, what you do have is of course, the Hessian matrix, and you can do a local analysis.
But they get the Hessian by kind of assuming you have an elastic network.
Well, you can define the Hessian by, because you have forces between all the atoms, so you can define the second derivative of the energy with respect to any displacement of any particle. So getting the Hessian is, but it comes from knowing the interparticle potential, which is essentially like the interaction between two. But they're not, why, is there an assumption in this that they're particular kinds of interactions?
I mean, in general, if I have the Hessian, I can't represent it by an elastic network, which is, I thought, what you were asking.
But I thought that's sort of what they were doing. Like,
well, this is not necessarily, and I think, if I understand by an elastic, so you're talking about a spring network. Here, it's not technically a spring network. I mean, the potential is a sort of Leonard-Jones potential, so it's a nonlinear spring.
But they calculate the Hessian matrix, which means they essentially map it on the spring network. Because that's by definition.
Yeah, otherwise the Hessian doesn't make sense. It's sort of assuming that locally it looks like a spring.
I mean, the Hessian's just the second derivative of the energy. As long as you could define the energy and it's differentiable, you can define the Hessian. I don't see why that you need to.
But that means that essentially you are thinking of the system as a collection of masses and springs. I mean,
in some degrees of freedom, but not the actual nodes that you have. That's the point.
I was curious, what are the colors there?
So this was, so what Lisa had done was she had set a cutoff criterion for which atoms were participating disproportionately, and then she had a second stage where she would say, try to find a percolating network of these atoms, and then divide them into what she called soft spots. So the idea was that this was one soft spot, and this was another, and this was another. And then when she was looking for correlation, she was very strict with herself about having the region that rearranged correspond to one and only one soft spot, which I think is a very strict criterion and kept her correlations rather low. And in my estimation, the places you get deformation do correlate very highly with the atoms that participate disproportionately in the low-frequency eigenmodes, but the ability to cluster them and know which are discrete soft spots, that's I don't think that was successful. That's hard.
Were you asking about the states of self-stress in this? Was that the question? Or?
They might not be exactly states of self-stress, but yeah, that was the question.
But that's also a linear response.
It is a linear response.
So that doesn't distinguish it from the Hessian way of, I mean, it's not the Hessian exactly.
It might give like a cleaner way of kind of identifying regions. I don't know, maybe it's the same, but this seems like it has like a lot of different steps, and seems like you make a lot of different sort of.
There are a lot of choices about how many modes do you pick, what is the cutoff for disproportionately participating.
Right,
there are a bunch of choices.
Right. Whereas if you really know like where are the places of concentrated stress, that might give you more direct.
But I thought the problem with that was that there was always a degeneracy of how many different ways you. I mean, the state of self-stress isn't unique. You could have rewritten it in terms of a bunch of other
so I think
states of self-stress. I mean, that is, it's not a.
Yeah.
So that it
but
doesn't
I
give
think
uniqueness.
you wouldn't have exact states of stress here anyways. I think you take the Hessian and you take its square root and then you multiply the square roots together in the opposite order, and this gives you like another matrix, and then you can find the eigenvectors of this other matrix, which correspond to like forces on all the sort of bonds between particles, although they're not really bonds, I guess. And so this, if you don't have any exactly zero eigenvalues, but you just have small zero eigenvalues, you would still get distinct eigenvectors. I mean, maybe they'd all be mixed up and that you can't really distinguishing them isn't.
So while I do think there's more work to be done here, there have been a number now of different sort of linear response metrics proposed to try to pick out where you're going to get deformation. And I think they all show some promise, but none of them are sort of a smoking gun. So I do think there's potential, for.
Yeah, so I guess, but whatever you do at this level, in terms of looking at soft spots, the connection to plasticity would at best be an observation which doesn't really have an explanation, right? In the sense that.
Right. There's another step there to understanding why does this linear response metric correspond to the place where
you can't really sort of invoke any kind of Lindemann criterion, because that only applies if you treat the system as homogeneous. If it's not homogeneous, the soft spots will have particles moving more. That's what it means. To have a soft spot. So, and one might even sort of say that if you have a soft direction, application of external stress the system will
concentrate in a particular direction.
And so the prevalence of plasticity along those directions is simply a fact that the system will respond by moving in that direction, rather than any connection between the softness and.
Right. So I mean, I guess there's the question
to rearrangement.
Yeah. Are the saddle points sort of ubiquitous? And wherever you get pushed in a particular direction long enough, you'll find a saddle point. Or are the saddle points very special? And really, where you may get pushed very far in a particular direction, but you just don't find a saddle point in that direction, and the fact that it's soft is really irrelevant, right? So here it seems to be indicating that there's some relevance to the softness, the local softness, but that it may not be enough to fully specify where the saddle points are.
Right, no, but I said this observation, I can, again, this is all at a very hand-waving level, but I can sort of explain this quote by saying that if I have a soft direction, when I apply external stress, the system will preferentially move in that direction, because
right, but that doesn't tell you that it'll necessarily undergo a plastic instability.
No, but if I preferentially rearrange along a particular direction, eventually when there is a plastic rearrangement, that's the axis along which I'll see it. And so there's nothing special about it being a soft spot in a soft direction. It's just, except that the system will respond to external stress by moving preferentially.
Right, but I think the interesting part of this work, and what Lisa and Andrea I think did show, is that there is some interesting correlation here that maybe you wouldn't, beyond what you would just expect of it moving more because it has some enhanced linear response. That's my takeaway. Anyway, So we had tried to see whether there were correlations between this soft spot measure and different kinds of topological order, right? Because the simple thing that people like to do in the material science community is you try to characterize what is the local structure like, what is, is there sort of a local crystal-like structure or other kind of structure? So you pull out an atom and you pull out all its neighbors and you look at the coordination shell and what is the topology of bonding. And you can characterize all those different topologies of bonding, and then you can ask, well, are the ones that are more like icosahedra harder and more difficult to deform, and the ones that are more disordered, easier to deform? And that does generally tend to be the case. These sort of very disordered structures tend to be more deformable and correlate with the soft modes more than the more ordered icosahedra-like structures that you can see in metallic glasses. But you can see the correlation is quite weak. So these gray represents the very disordered structures, red represents the icosahedral-like clusters, and the participation fraction is to what extent did they participate in very soft areas. And you can see that there's a correlation between these things, but it's not enough to pinpoint where defects are, in my opinion. So let me jump into what we've been doing lately. So this is the work by Sylvain Patinet, and this is a much more direct attempt to locate the defects. So what Sylvain will do is make, in his case, a 2D binary Leonard-Jones system, make a block of this stuff. Yeah, I'm sorry?
That was originally proposed in the 2010 class.
Before the 2011? Okay, we thought we tracked down the earliest one. By Peter or by, okay, yeah. So this was a proposal originally by Peter Solich. And so the idea was you take some region of the glass, you put a frame around it. Basically constrain everything outside that frame. And so we're going to constrain all the atoms, all the yellow atoms. And then we're going to impose some deformation. So we're going to deform that region, letting the green atoms, the ones on the inside, rearrange, accommodate to that deformation. And then do that slowly until we see some kind of plastic instability. And so we have to choose a length scale for that frame. How big is this region you're going to allow to deform inside the frame? And there was some prior work that had proposed that for this Leonard-Jones system, I think it was 5 atomic diameters, is the length scale on which you recover elasticity. Like if you're smaller than that, you really don't have Hookean elastic response. But if you're larger than that length scale, you have inhomogeneous, but basically Hookean elastic response. And so we chose that length scale, and we then tested different length scales. That ended up being a decent length scale. So when we do that, what we're measuring is, along different orientations, what is the stress we have to impose to get a plastic event. And we're constraining it to be local, right? Because everything outside of this is just not allowed to happen. And we could do that in different orientations. So this is the kind of map that Sylvain produces. So here, the scale is the local yield stress. How high do you have to ramp up the stress on a local region before you get a plastic instability? And you can see we have these yellow regions which have very low local yield stress. And then around those, we have other regions with slightly higher, and then regions that have relatively high local yield stress. They're not very deformable. And your eye immediately picks out essentially the length scale of the probe, right? That you can see that there are these regions that are about the size of the length scale of our probe that seem to be quite distinct from each other. And then what Sylvain can do is do athermal quasi-static shear again, so not dynamics, zero temperature, essentially energy minimization shear, and look to see in different orientations what is the first place that deforms in this material. And you can see those are the teal circles, and those correlate quite well, and I'll show quantitative data on this in a moment, with the yellow circles where the yield stress is low. So this is like a brute force measurement of the local yield stress. And you can see what look like quite local defects. So this seems like good news for the STZ picture, that there do seem to be quite distinct regions that are more deformable than the regions around them. So one issue that comes up in the metallic glasses literature is that there's this idea that you can describe the local structure through something like a free volume, the idea that the density must control the behavior of the system. But of course, density is a scalar quantity, right? And so if free volume were the only piece that was interesting, then you would expect that if something has high free volume, it's as likely you could deform it probably in any direction. There's nothing about free volume that picks out direction. But here what we're doing is cycling through the local yield stresses, yellow being low local yield stress, along the different orientations of local solicitation. So you can see, and the square in the middle shows the kind of deformation that's being applied locally around each probe as it changes shape. And so you can see that regions that are highly susceptible to shear in one direction are not necessarily highly susceptible to shear in another direction. That these defects certainly have an orientational character to them. So they seem to be both local and they carry orientational information, which is important for storing information like that we saw in the Bauschinger effect earlier. Okay. We can also see distinct differences between materials that were quenched quickly and slowly. So you can see many more local low yield stress regions in the quickly quenched glass, the glass where the temperature is lowered very quickly from the liquid to the glass than the slow quench. And then the circles here represent when we shear the system continuously, where is the first, second, third, fourth, fifth, sixth, seventh, etc. event as we shear the system. And you see even out to the 10th event, the low local yield stress measured in the as quenched system correlates well with where we're getting deformation. So it's not like every time you have a deformation event, your whole deck gets reshuffled and you have a new set of defects to worry about. The defects do seem to be embedded in the structure and they persist. So we've quantified that. So this is a graph of the correlation between the structure as measured in the original as quenched material and the places where we get deformation. And here we're comparing different measures of the local structure, different attempts to measure where the system will deform. So black is the local yield stress. That's the measure I was just showing you. PF is participation fraction. That's the soft modes, using the eigenvectors to pull out the soft modes as I was talking about earlier. 2 mu is the lowest local shear modulus. PE is the potential energy per atom. Yellow is the short range order topologically measured measure I talked about before. Rho is the local density. And the blue line here is what you would expect for just random white noise. So basically what this is saying to me is that you get quite good correlation with the initial structure out to 75 or 50, depending on the quench, events, right, for the participation fraction measure, and that the other measures don't seem to do as well at predicting where you're going to get deformation, but they all except density seem to have some relevant information. It's not that they don't carry any information about where you're going to deform, it's just that they don't have the whole picture.
Well, the 75 or 50 itself doesn't have any meaning.
Yeah, I mean, it's for the given system. So this dashed line represents, I believe it was 7% strain. Yeah.
That's the yield strain.
Yeah, right. About where the peak is in the stress strain curve. Where do I have the? Yeah. Yeah.
Then how come there is? I'm sorry. Now, how come there are correlations even going beyond that?
Because I think you still, like, for example, in the quickly quenched region glass, you shear the system, actually it tends to localize a bit. So there's a region that's highly deforming, that's probably entirely been remodeled and has no memory of the original structure. But then you still have some deformation going on outside the shear band where you really haven't fully remodeled the structure.
Did you also look at distributions of the local
Yes,
stresses?
I think I have that. oops, I guess I didn't put that in here. Yeah, we can measure distributions of the, so that's the nice thing. We can look at distributions. We can look at distributions as a function of orientation. So we have histograms of those distributions.
And do you know what they look like? Do they look?
Yeah, they're, I mean, too bad I didn't put them in. They're in the paper, but yeah, they seem to have a power law tail going to 0. And then they have a peak, and then they drop off at high yield stress as well.
And that power law is related to this other thing from Weir?
Not that we know. We seem to get very different power law tails than the wired prediction.
Very interesting.
Yeah, and it seems to depend on how the glass was prepared. It doesn't seem to be very universal.
Okay.
Yeah.
Yeah, nice.
Okay, so that was my summary of the STZ part. So just let's see where we are. So that they can be detected and characterized with atomistic simulation, that we seem to be in a good position now to ask how the STZ population evolves, since we can pinpoint where we have these low local yield stress regions, what the distribution is, what the orientation is. And so we're hoping now to take the next step and use this to compare the direct measurements of the defect structure to the theories and where we see deformation. Yes?
So I have a question and a comment. See, all of this, okay, so I guess very few people would doubt that when you begin to strain a sample, there would be localized effects. But because you have this elastic interactions that are long range, there is a question mark about what happens as you approach the yield point. The interactions between
start to create correlations.
Is important, is the transition cooperative in that sense. So based on what you have done, what would be the answer? That's one question.
Okay.
Also,
put that in the parking lot.
There are some sort of ideas about the yielding transition which say that there are avalanches that are diverging in size approach the yield. And this would clearly, depending on what your answer to the first question is, you may or may not be consistent with that.
Right. So first of all, I don't think that this question of like, are they local events, are the defects that control plasticity local, it doesn't really answer the second question. These are distinct questions. So, but I think there is evidence in the simulation literature that, yes, you do start to see, mediated by the elastic field, correlations between triggering of events. I mean, we certainly see that in our simulations. Now, there's a sort of other question in there, which is maybe how important is that, right? Because, we know for these materials, shear banding as the failure mode, right, where you have local deformation concentrating into a single region in the material, is critical for how these materials fail. So if that phenomena leads to shear banding, then it's very important practically, right? It may be interesting anyway, but then it would be very important practically. But I think that, and this is sort of in the second half of the talk, which I'm not sure how I'm going to get to give, that the local correlations lead to, avalanche-like events where STZs trigger other STZs. But I believe this is quite distinct from the shear band, right? That it's the fact that these events also soften the material that leads to the shear banding, and that's distinct from the elastic correlations, or at least that physics can be captured potentially without including the elastic correlations.
I'm grumpy a little bit. But maybe I should keep quiet for a little. Seriously, our original idea some years ago, work that I did with Lisa, was basically, you haven't mentioned the effective temperature at all.
Right, that's the second half of the talk, which I'll probably never get to give.
Okay, then why don't you just go on, and I'll grump later.
Okay.
So one other question about the first half of your talk. Now, so I recently heard this story about shear transformation zones, interpretation in terms of geometric elasticity theory from this group of Eran Sharon at Hebrew University and his former student Michael Moshe, who's now, I guess, a postdoc with Mark Bowick. Are you familiar with this work, and if so, do you find it useful?
Yeah, I just tangentially. I can't say I've studied it in enough detail to. My understanding is that they say, because all of these materials have a residual stress field, right? And so, and there's a question: how important is the residual stress field to where you trigger events? I think it ends up being the secondary effect. But anyway, you could imagine modeling that residual stress field by having a manifold that's sort of constrained into a lower dimensional space, and then that would also produce a residual stress field. So I think that's an interesting way of thinking about the residual stress field, but I'm not sure it makes a direct relation to plasticity. So, yeah. But I really don't feel fully like I fully informed myself about that theory yet.
Just one question. In your simulations here, are they overdammed, underdammed?
These were all athermal quasi-static, the ones I just showed. Yeah. So, okay.
And one last question. For your distribution of these local yield stresses, presumably that changes once you've developed a shear band?
Yes, it changes as you shear.
Great.
Yeah.
Great.
So you had this orientational dependence on where you found these local soft places.
Yes.
Did that play out when you sheared the bulk?
Yes. Yeah. In fact, in order to do the correlation, the quantitative correlation, we specifically looked at not just the low local thresholds, but sort of the resolved stress along the direction of the applied shear stress to the local yield direction. So it's sort of like, if you're familiar with dislocations, like the Schmid effect on the dislocation motion. So anyway, but it's like basically the resolved tensor along the applied shear direction, because they have an orientational dependence. Yeah.
Okay, last question. When you have a shear band, then the distribution of the threshold yield stresses goes to constant, no longer to zero. Is that right?
Right. Then you reach a steady state inside the shear band. Yeah.
Great.
Okay. So the second question I wanted to talk about, I should keep in mind. Okay, we have 30 minutes. We've been having a lot of discussion along the way. I think that's okay. So there's this question that I brought up along the way. Is there a scalar quantity that governs the defect density? I think this has been a big question in the field for a long time. And the scalar quantity that was sort of the scalar quantity that most people talk about in the engineering community has been the free volume, which I'm not a proponent of. So and for reasons that I just showed you, I mean, when we look to see whether anything like density correlates with where you have deformation, we don't see any correlation, and furthermore, I'm not even sure how to define this and measure it properly, because I don't think it's only really well defined as far as I know for hard spheres. And these are not hard spheres. So what I'm going to talk about is the effective temperature theory, which Jim talked about a bit yesterday. So I'll talk about this in the context of the glassy materials. And there have been other sort of quantities proposed, like bond ratios in amorphous silicon. But the questions I want to ask are, do the simulations and experiments of shear banding, so looking at this failure mode where we get localization of deformation in a particular region of the material, do they bear out the hypothesis that this effective temperature idea would work? And then eventually we could ask whether these things are interrelated. But yeah.
Sorry, why do you expect it to be a scalar quantity since you just discussed the orientational dependence?
Right. So now we've okay. So clearly it can't only be a scalar quantity that's at work here, right? The fact that we have Bauschinger effect must mean that there's some tensor part of the local state variable. But you know, what I'm saying is that in the literature already, there's this idea that perhaps there is a scalar quantity that, if it doesn't describe the orientation of the STZs, at least gives their density, gives an idea of how many there are. And so that's been in the literature for a very long time, since Cohen and Turnbull. And so what I would like to say is, at the most basic level, we would want to talk about populations of STZs, but of course, that's difficult, right? To try to describe, eventually, for engineering purposes, you don't want to have to describe everything in terms of the full population of STZs and where they are. So if there are other quantities like the STZ density that are useful for describing the local structure, I'd like to know how they are and how I can relate them to thermodynamic quantities. And so the effective temperature idea is that basically the STZ density should have a relationship to a structural temperature associated with the glass. And so,
if you look at sort of other attempts of this kind, in granular matter, I guess the corresponding quantity is this angoricity.
Right, yeah, that's
quantity. But the point is, if once you have it, you can always define a corresponding scalar quantity that captures some part of it. So how do you, what's the question to be resolved is a bit unclear, I think. When you put the underline on scalar, then these questions.
Right. So maybe a better way of asking this question is, okay, we have a system, it has defects. We want to understand the dynamics of those defects. Is there a non-equilibrium temperature for this system? That would be a scalar. Yeah. So I'm going to think about this temperature. So the idea is I'm going to make the assumption that a glass has two different separated time scales. So this is an assumption. That it consists of a fast vibrational subsystem that we could measure the temperature in the usual way, just put a thermometer next to the thing, and that the temperature there is defined as the derivative of the energy with respect to the entropy of these fast degrees of freedom. But I'm also going to imagine that the bonds of the glass are also something that's changing when I shear the system, when I undergo plasticity or anything like that. And so I want to think about the bond network in the glass. And just like I could ascribe an energy to this system, clearly I could describe the bond energy in the glass. That would be pretty easy. Perhaps also I could think for glasses at this energy, how many different ways could I reconfigure the bonds to make that glass have that energy, right? And in that way I could think about it having an entropy in terms of like how likely is a bond configuration at that energy. And then if that's true, if I could think about the entropy in that way, I could think about taking a derivative and defining something that at least has the units of temperature and maybe is an actual temperature of this slow configurational subsystem that's weakly coupled to the fast vibrational subsystem. Okay, so that's a cartoon of course, much more involved theory. But so how am I going to deal with this in terms of the simulations? So what I'm going to say is that, in a real thermalized system, I could typically define for a given system a specific heat, and then if I wanted to, if I had a change in temperature, I can relate that through the specific heat to the change in the energy of the system, right? So what I'm going to assume is that for the configurational subsystem, I can also define a similar specific heat. And if that specific heat is fairly constant, then I could infer a change in the effective temperature from a change in the energy of the system, from change in the bond energy. And the reason why I'd like to make this ansatz or use this ansatz is because it's very easy for me in simulations to measure changes in the potential energy and the bond energy of the system. I have no direct way of measuring the effective temperature. So I'm going to measure changes in the bond energy, and by saying that there is this specific heat, which I'm just going to use as a parameter, then I can infer the effective temperature. So basically, I'm going to talk about the effective temperature, which is going to be this quantity de-dimensionalized by an energy to create one of these defects, one of these STZs, multiplied by KB. So this way I get a dimensionless quantity. So basically this dimensionless quantity, which I'm calling chi, which is like my de-dimensionalized effective temperature, is just linearly related to the potential energy per atom. And that's how I'm going to pull it out of simulation.
And potential energy is just, you're just taking the total potential energy at any instant of time. It's not a T equals it. You're not asking what the underlying ground state would be. Just
right, because I'm only interested in differences. Like I'm subtracting off some constant here, which may be immaterial, but I am going to subtract off some constant because I know some of that is, I don't know what the reference point is. And then there's a prefactor. Right, but but there was a point here that I was. Sorry. Repeat the question.
He's asking sort of about, is it important to know what the inherent structure is?
Oh, right. Yeah, so we're just going to, yeah, I mean, but that's, okay. Yeah, so it's fairly easy for me to measure a reference potential energy. So we try to infer this reference potential energy and we subtract that off, and that's how we get rid of the inherent structure. And then we do sometimes take off, because we want this to just be related to the plastic changes to the material. So of course elastic strain would also raise the potential energy. And this is not meant to measure elastic differences, right? Like stretching the material shouldn't raise the effective temperature if the stretching is just elastic. So we do sometimes subtract off the elastic component. But otherwise, it's a sort of quick and dirty way to try to get at something related to the effective temperature. And then the assumption in the theory is that the density of the STZs is related through a Boltzmann-like relation to this effective temperature. So, question?
So you're I'm not sure I understand. So you're deforming your system
and you
calculate the change in energy relative to some undeformed state, and essentially you call that the temperature.
Yeah. So what I'm going to do is I'm going to deform some systems, look at how the potential energy field of the system is changing as I deform it, and it's going to localize. And I'm going to try to make an argument that I can infer the effective temperature.
What do you mean it's going to localize?
I'll show you, we're sort of getting ahead of ourselves. So give me two more slides to try to answer that. Yeah.
So if you have a system which is sensitive to the direction of the deformation, then it seems like you're going to get a temperature that's also sensitive to that. And so your temperature might actually become a tensor. I mean, it certainly is a tensor.
Well, the fact that you have a temperature degree of freedom doesn't mean that there are no other important degrees of freedom, right? I mean, there could be
I'm just saying you would, depending on how you apply the strain that you're going to apply, you might get a different answer.
Well, the effective temperature pertains to the irreversible deformation.
That's okay. But I'm asking about direction.
I understand. And you, in fact, may want to calculate that the effective temperature then depends on space and direction and things like that. And that comes out of these analyses.
But it's not a scalar necessarily.
No. Well, it is a scalar, but a scalar can depend on have spatial dependence.
Okay.
Right, but I'm not conceptualizing it though as something, because from the basic definition, if I were to say the temperature were a tensor, then that would have to mean either the energy or the entropy is a tensor, and I don't know what that means. But.
Am I holding back again?
No.
She.
So, yeah.
She wasn't jabbing me.
But just because there's a temperature doesn't mean that there can't also be like a bias in the defect field that carries tensor information, and that's also important in some instances in addition to knowing the configurational temperature. Anyway, okay. That's my best answer for now. So we have a constitutive theory that's based on this effective temperature. And the constitutive theory is here. It's just these two lines. So we have a plastic strain rate. The plastic strain rate depends on the number of defects you have, which I said is proportional to e to the minus 1 over chi, and proportional to a rate at which they undergo their transitions, which I'm just going to write down as some function of the stress that goes to 0 at some yield stress. So if you get the stress above some threshold, they start to flow. And then I have to define also how the effective temperature is changing as I deform the system. So now I have the rate of change of the effective temperature depends on the local rate of plastic work, right? If I'm doing work on the system, some amount of that work is going to raise the temperature. It's going into the structure to disorder the structure. And then I have some ability of that temperature field to diffuse, just like a temperature field typically diffuses. The difference here is that the rate of the diffusion constant, is also related to the rate of plastic deformation. And there's some length scale that has to come in here that has to be something like the defect size. Yeah?
Just briefly, I mean, this diffusion term assumes a simple-minded diffusion coefficient, whereas if the mode of diffusion is through long-range interaction,
right?
Then this may have to be something else.
Right. This is the simplest thing kind of we could think of where the well, you could imagine just putting a constant diffusion term, but that doesn't make sense because you don't really have these things move. The material doesn't do anything unless it's being sheared, right? In this at low temperature. So
I mean, it's not constant.
So this was sort of just the simplest thing we could think of.
It's not dependent on space.
This is because the plastic strain rate's dependent on space. It's not necessarily deforming the same everywhere, right? This depends on location. Chi depends on the location. Okay, so this is the thing I'd like to do. So I'm going to do a simulation of shear banding. I'm going to take, in this case, a copper zirconium system, so a three-dimensional binary metallic system modeled by an EAM potential. I'm going to create an initial condition. So this is what I typically do, like quench the glass. I then do a shear simulation. And then what's the information I get? I can get out the stress-strain response. I can look at the stress-strain curve. And then I can look at the microstructural evolution. And then I can look to see how does the potential energy in the glass change at various locations as it's being sheared. And it's going to form a shear band. I'll show you that in a second. And then what I'm going to want to do is take that atomistic initial condition and use it to create an effective temperature field, right? So I have a different effective structural temperature at different locations in the material. Some places are more disordered, some places are less disordered. I can measure that through the potential energy per atom. Then I can apply the equations on the prior slide, the constitutive law, using a code that was developed by Chris Rycroft. So we do this STZ theory simulation, and that also gives us a stress-strain response and a picture of the microstructural evolution. How did the temperature field evolve? And then I want to compare those two. Does the theory predict the same thing that we see in the molecular dynamics simulation? Okay. So what I'm going to show you here is one of these simulations. What we've done is coarse-grained the simulation. So here, this is a picture where we've coarse-grained at some length scale. You see these voxels are colored according to whether the local voxel has a strain above the nominally imposed strain or below. So initially, it's sort of just going to fluctuate randomly because you have some elastic waves moving through, and it's all basically deforming elastically. It's pretty uniform. And then eventually, you'll see it'll localize in the center. This shows the histogram of the potential energy for the material inside and outside the shear band, in the blue region and the yellow region. And then this shows the strain in the system, the potential energy in the system, and this is the simulation with Chris's code. So this data, all this data is from molecular dynamics, and this is a continuum simulation. So you see here it's just fluctuating around. We're at 4.5% strain. It's more or less behaving elastically. The potential energies are all sort of indistinguishable from each other in the two regions. Then around 9% strain, you'll see localization develops. The potential energies in the two regions are quite distinct, right? The two regions separate. So you have the material inside the shear band, the material outside the shear band, and here you see the strain is localized, This is the potential energy per atom is significantly higher inside the shear band than outside the shear band. And then the theory predicts also localization at nearly the same location. So this is a good time for me to maybe go back and see if I
don't understand the probability plot.
This is to see how Gaussian or non-Gaussian these. This is. I don't.
You don't need to. I don't need to know that.
Don't worry about it.
Yes.
So you were asking about whether whether it's localizing or hopefully this answers that question. That the temperature field, the potential energy field, and hence the temperature field are highly inhomogeneous once you have the localization, and that corresponds to the localization in the strain. Okay. So what we've been doing is we want to be making this connection between the atomistic simulation and this continuum picture we're trying to develop.
The atomistic simulation is a realistic simulation.
It's
not AQS.
It's in this case, it's not AQS. It's low temperature MD.
Okay.
But AQS will give you the same.
I'm sorry.
Well, this is the problem.
Yeah, there's a thermostat. You have to. Yeah, there's a Nose-Hoover thermostat.
It's overdamped?
It's probably in the overdamped regime. So yeah, maybe. So one of the interesting things here is that in order to make this connection between the continuum simulation and the atomistics is we now have to struggle with this question of coarse graining. How do we coarse grain the atomistic system to be able to compare it to the continuum simulation? And so in this case, what we did is we used a Gaussian windowing function in order to coarse grain the atomistic simulation. And so the first thing I'm showing here is if we coarse grain at different length scales and we look at different applied strains, so the strain is going down as we is going up as we go down. So here this is unstrained, fully strained, and then we look at the histograms of the material that's over the nominally imposed strain and under the nominally imposed strain. You can see for small coarse grainings, the two histograms separate, right? They both look pretty Gaussian. They separate, but they're still heavily overlapping even at the highest strain when we're really heavily localized. For a much coarser coarse graining, they're indistinguishable. Then when we localize, you see the two distributions are quite distinct, right? So there's an issue here in that how do we choose the coarse graining so that it's picking out the length scale at which we care about the variations in the structure? And so this is showing what the potential energy per atom coarse graining looks like for different lengths of the coarse graining. And this shows the stress strain curve that we get depending on the coarse graining applied. And you can see that only when we do the coarsest coarse graining that we can apply do we get stress strain curves that look like what the MD produces from the continuum simulation. Whereas when we choose the coarse graining too small, essentially there's so much noise in the system, we miss the important signature, or the important changes in the effective temperature over the local fluctuations, and we start to get stress strain curves that don't really reflect what happens in the MD. And then this is the last slide, I think. This is the coarse graining of the potential energy field from the MD. So these are all the same simulation, just coarse grained at different length scales, going from 0% strain to, I think this is 50% strain or something. And then on the right is the translation into the continuum and then the continuum simulation. And you can clearly see that if we coarse grain too finely, there are all these fluctuations in the potential energy field and hence the effective temperature field, and so we don't end up getting localization that we see in the MD. Whereas if we coarse grain above 32 angstroms up to 50 angstroms, then we start seeing behavior, much more similar behavior between the MD and the continuum simulation. So that's. So I think what we're getting at here is that we can do some reasonable cross comparisons between molecular dynamics simulations and continuum simulations from the theories that we've proposed. They rely on a number of assumptions and ansatzes, but I think they're more or less reasonable. And that we're now struggling with this issue of coarse graining. How do we properly coarse grain? What is the proper coarse graining length scale, and where does that come from? And I think we have a lot of open questions about the model and the parameters and things like that. But I'll just leave it there. So, thanks.
Look, the really interesting questions which you're touching on here, and I'm sure Karen is going to tell us more about, is the shear banding. It's an instability. Mm-hmm. It shows up when what you do is you have somehow started with a system with an inhomogeneity in what I like to think of as the disorder of the material, effective temperature in those languages. And the question is, there's an instability that you can sort of understand. It comes out of the theory. You see it in this, because in fact, what's happening is that the shearing is more rapid, stronger in a region, and that then triggers getting stronger, because as the faster it goes, the more it disorders that local region, and it leaves the rest of the system out of it, and therefore you get the shear banding instability, which in fact is very similar to what I was showing in a completely different system yesterday.
Right.
And we know that that's the physics, but there's this other kind of physics that talks about, we have localized STZs, if you like to call them, localized shear zones that can interact with each other elastically, and that sort of deterministic dynamics can actually dominate in some limits. Now, one of the reasons that I really am unhappy about anybody doing these kinds of things with a thermal, essentially stationary, quasi-stationary, is that what you do when you do that is that you say, oh, the actual atomic dynamics is irrelevant. Atomic lengths, time scales, I'm throwing them all out. And I'm making a completely artificial zero temperature. It's not just zero temperature. It's forgetting the dynamics of the interactions between the molecules. And I think you get wrong answers when you do that. And that's why I was particularly. You're unhappy.
Yeah. Well, I mean, I think first of all, in the instance of using the athermal quasi-static to do the defect detection specifically, I think there it's certainly clearly defensible, because you're just trying to understand something about the structure. So you're probing something about the inherent structure of the underlying material. Then there's the question about, okay, when you do the shear, how much do you... And I mean, I agree that there are definitely things that athermal quasi-static can potentially leave out. But it does capture, I mean, all the potentials are there. The relaxation associated with elasticity is there.
What's missing?
You won't have thermal relaxation of anything.
No, you won't have that, nor will you have the fact that while an event is happening here, another event could occur somewhere else that interferes with it.
That can happen.
Not in AQS.
What
AQS is when what you do is you just look at the positions of the atoms, and now you make a very incremental deformation, a shear, and as soon as something happens, you stop shearing it, and you let that thing relax locally.
So quasi-static.
Yeah, quasi-static.
That's just
Exactly right. And what I'm saying is that when you have these more interesting systems, that it's this competition between timescales which are completely left out of the AQS.
But we don't see anything qualitatively different when we do these things at finite temperature.
Well,
we don't see anything qualitatively
but what I'm saying is that this is the question. My eyebrows go up when I see, because there is a fact, in fact, that must be a regime in which this banding mechanism isn't the right one, where in fact what's going on is that I have interactions between
elastically triggered events.
That's right.
Yeah, and I think you can get that even in the athermal quasi-static. There's no problem. Well, all you have to do to get into that regime is either quench the system extremely violently, or shear it until it's in the steady state.
What I'm asking, and I don't know the answer to, that's why I think it's particularly interesting, is how do we distinguish between these regimes? Here, you've posed one that I sort of like, and you can blame me partly for, but we know that there are other things that happen when we have noisy systems that are on the threshold of going from elastic to plastic behavior, and we know that all kinds of noise happens. How do we understand that? Which of these theories, which of these descriptions is the right one for that? And that's what I'm sort of hoping that you guys will tell me about sitting these times.
Is it that mysterious? It doesn't seem that mysterious.
Make a comment on this point. Now, in terms of whether AQS is a good description or not, surely there are going to be phenomena where thermally induced relaxation processes are going to be both important and sort of working on the same time scales as the mechanical processes that you're talking about here. But isn't the whole picture of having a mechanical temperature telling you that in fact there should at least be questions that you can address without getting into what thermal effects are going to contribute, right? Isn't the assumption? Sorry?
You finish your statement.
So, so if I look at a sufficiently cold glass, nothing's going to happen if it's left to temperature, right? The only processes of interest that are going to happen because you're loading the system, right? So under those conditions, it seems to me that time-dependent. There will be time-dependent effects where obviously time matters, and you don't have it in AQS, right?
That's what I'm pointing.
Right.
That's the important point.
Yeah.
It isn't whether there's temperatures.
Yes, it's a time.
It's whether you're getting the relevant competing time scales into your problem. And that's what I think you're not doing often. Right? You do AQS. Sometimes you can get a caricature of it, like you're probing the system just to see where the flow defects might actually appear. But if you're actually interested in the interesting phenomena, like these shear banding phenomena, which are failure phenomena, then I think you have to be much more careful. And it's just because what Sri said is that you're really pretending there are no time scales in the problem, and that just can't be right.
And that's, all the simulations I just showed you were not AQS. All the effective temperature, they were low temperature MD simulations, and we're currently doing shear banding simulations at finite at 300K. And there are important time scale issues that I think are emerging. We're still trying to tease that out. But it becomes much more complicated.
Yeah, no, I think there's no argument about this, that there could be time scales that are important that are left out in AQS. But I'd also like to sort of emphasize the contrary, which is the counterpoint, which is there are questions you can ask where time scales are not particularly relevant, and you can look at an AQS based. You can use AQS for those things, but if you do worry about time-dependent phenomena, then obviously it's not going to tell you anything And it could be misleading if you don't do it.
But what we're interested in here is an instability which is by definition a time-dependent phenomenon, and it can be not at all properly described by our wonderful effective temperature theory, or even a disordered temperature theory.
So I'd like to share maybe so like a point of order. This particular topic,
yeah,
I know is of great interest to some of us, and it includes me. And I'd like to have more time, but probably it's not a point for
the general
discussion. So shall we, when such situations arise, shall I just send an email out saying some of us will meet at some time to talk about this particular topic? Anybody who's interested can join. Is that a good way to do it?
That sounds great.
Yeah, but
so,
I may not be able to come all the time. That's the point. I'm
no,
not away from home.
No, your schedule. No, but I think shear banding.
Yeah, let's have a separate discussion.
Time scales are important. There is something that I would like to discuss. And I guess Karen and Michael.
Is Wendy Wright going to
So can we find a time next week to sort of talk about this?
Yeah, that would be great.
So I have some what I think are interesting results from AQS simulations of shear banding.
Okay.
So did you want to say that?
Yeah, I just want to say one thing. You said something at the very beginning, but maybe considering that this is a workshop on memories, and so now that you've given the talk, where do you think the memories are coming into this? That is, you talked about all of these aspects. I think I've lost a little. I mean, interesting as they are, but I've lost a little bit about. Okay, so where were memories? What was it that was remembered here? What was it that you can read out from memory? What was,
Right.
So where did that go? I mean,
yeah.
Why do you think you must be thinking that this is really relevant to memories? And maybe you could just say something about that.
So I think there's what I think I learned from this at this point is that there's actually memory on two different length scales. There's the defect populations, which I think we can now measure, where you both have things sitting at a particular location, and you have distributions of them, and they have orientations. So in principle, you could measure out where they are, what the density is, and what is the net orientation of these defects. So those are measurable. That's on a very small scale. But I think then the second half of the talk is really saying, well, but for the purposes of the failure mode, the actual length scale that's relevant is not actually that length scale. It's actually a larger length scale at which I think this effective temperature field dominates. Basically how the density field is changing that determines where you get failure. So if one could measure that effective temperature field, that's another way one might encode information in a glass, have a high effective temperature region, a low effective temperature region.
So I guess, one other way of saying it is, if you are thinking about, broadly, you sort of thinking about thermal effects and mechanical effects and looking at how you might imprint memories in these kind of systems, right? Doing something mechanical. And I guess, you didn't sort of, I guess this is what Sid is asking, you sort of showed results to say, here is what I can read off from the structure, and here is how I can describe what mechanical treatment of the system is doing. But I guess what you're asking is, can I then think of it in the language of memory to say, this is how I can imprint and read?
Yeah, as an example. What is imprinted, what is read, what is erased,
right.
So
for example, the effective temperature idea. If that's generalizable beyond this whole shear band context, you could imagine having a glassy disk or something, and having a heated probe that you use to poke the disk, heat it very rapidly in a very small area to bump the effective temperature up to a high level by essentially rapidly quenching it, or bring the read head over, or write head over, and slowly anneal that area to get it to be at a lower effective temperature. So that would be one, if you wanted to generalize this to something that would be like a memory storage technology, that's one.
It wasn't necessarily technology, but just what the...
in principle idea, yeah.
So the first part of your talk was very straightforward to me, in that you showed that there are these STZs, these defects, you can see them, you can measure them, and you can locate them. The second part seems then you had to introduce some additional structure of the effective temperature, etc. Why isn't the density of STZs by itself enough?
Well,
you have one field which is you can measure the density of, and this density can vary and give shear banding, and I can write equations that describe that density. Why do I need to introduce another concept?
Right. So part of this is a practical. These were sort of two projects that were proceeding on different tracks. You know, I think the effective temperature ideas are important to us because they underpin the constitutive theory that we've developed. But of course, now there's like the obvious next step, which is, can we go in and for the same system measure the actual defect population sites densities and measure the effective temperature field and show that.
But why do I need to measure the effective temperature?
Because I think the effective temperature field is more I think there's, from a practical standpoint, maybe I've been in the engineering world too long, we can do this thing in MD where we find the individual STZs by probing the system locally, but you could never do that in real life. I can't even imagine the experiment that would allow you to do that.
So, Michael, one thing, just to break that up a bit, in the theory that you wrote down, if I wanted to, right, I had one relation between the density and the temperature, and I can use that substitute for chi everywhere with the density of shear transformation zones, and I still have the same theory, nothing changes. Right? And now, in terms of the practicality of working with one concept or the other, if it was somehow a lot easier to measure the effective temperature than the density of the transformation zones, that distinction would apply. But I guess that doesn't...
Right, but the potential energy per atom, that's something I can measure by differential scanning calorimetry.
Okay.
So...
Yeah.
Mike, you and I may, although you're the one that invented this theory, but my way of thinking about it has evolved a bit since you've gone off in the real world on your own. And I don't think of the STZs, we talk about a density of STZs, but I don't think of those as being some permanent feature of the material. Okay, what the density of STZs and therefore the effective temperature is doing is a probabilistic thing. It tells it we have these fluctuations in this material, and what's the probability that some fluctuation is going to occur that will allow a rearrangement of the atoms locally. And so it's too easy to think about saying, okay, I'll look at this particular piece of material and I'll measure the density of STZs. It's not the way you want to think about it.
But we have this relationship that says, since we think the STZs are essentially the tail of a distribution, they're like the extreme structures in the material, we have this Arrhenius relationship that should relate the density of STZs to the effective temperature. So,
but I would almost rather not say density of STZs as probability of formation. Because the time scales, you get an STZ that really looks like an STZ, and it's going to very rapidly rearrange the atoms there and disappear. And that's what's really going on. And so it adds some confusion if you think that you're going to have some well-defined...
no, I think I disagree with you on this. Because if we're thinking of these things as defects, then at least at any given time, they have to be there in the structure.
Well, but they may be very ephemeral.
That's okay.
And in fact, the time scales on which they appear and disappear may be very short, maybe microscopic. The time scales that are long and slow are the time scales between those events.
So, yeah, I think there are 2 points. One is, whether you can look at a structure and count the number of these things, and to put it crudely, and we're sort of saying different things. And if it was sort of a structural feature like, 5 coordinated atoms in the system, this I can count, right? And whereas here, that's not the case. Maybe you can figure out how to do it. But the other thing is also, fundamentally, an STZ is defined as a response of the system. So I would say it's more easy to think of, for me, it's more easy to think of it in probabilistic terms, like what Jim is saying, because so that whatever you mean by the density of STZs is effectively the likelihood of a rearrangement happening.
Look, there's subtle points that can make a difference, however, in how you organize your calculations.
Nathan, do you still remember?
Well, the discussion's gone in a different direction, which I'm also interested in, but I don't have a question at this point.
Okay.
We should talk more.
Yeah.
I just have a comment which is connected with Sid's question. We are all going to talk about different systems and what memory means. So maybe it makes sense to, from the very beginning, try to make some sort of a classification of
this is tomorrow's
different
agenda.
memory. Okay. And then we'll talk about it tomorrow.
Well, we may not get through. I guess what we'll try to do over the different discussion sessions, because we'll see how much. Okay, so tomorrow, since that's probably a good note to end on, what is probably going to happen is, Sid will sort of start off the discussion by presenting some perspectives on what memory could mean in the kind of systems we're interested in. And as I said earlier, all of us should probably then make brief statements about what they think are the interesting problems, and in the subsequent discussion sessions, we'll try to sort of make it more organized and comprehensive.
But the discussion session is really supposed to be discussion.
Yeah.
It's not supposed to be a talk.
Yeah. No, that's why I'm saying probably what we will do tomorrow is not for you to present the full picture that Zorana was sort of referring to, but to sort of start the discussion towards developing that kind of a picture. So, but tomorrow I think an important part of it is specifically a request for all of you to come up with your sort of favorite ideas of what is interesting, what memory means in the systems that you're interested in. Maybe the following week, when we have the discussion, this discussion leader will try to present a more comprehensive picture, and we keep doing that. Yeah. Okay, I think that's a good place to stop. Thank you. Yeah.